Okay, thank you very much. We are starting our new session. This is Wednesday, July 8th, our first half of today's lecture. We're going to be continuing with Chapter 13, Part 2, Conjugated Unsaturated Systems. Okay, and specifically conjugated dienes. Okay, so with the conjugation comes different reactivity. And so we're going to start with our first and simplest conjugated system, which is our conjugated dienes, okay? So in our conjugated dienes, these are compounds that have alternating single and double bonds, okay? So we have to have a double bond, a single bond, and a double bond. So it's a pi, sigma, pi, okay? We typically call these 1,3 dienes, and they can be substituted, or they can be our simplest one, which is our 1,3 butadiene, okay? Now, by adding substitutions, we can change their reactivity and we also change their names. Okay, so we have with us a possibility of different stereoisomers. Let me grab my good stylus, there we go. And so we have the ability of doing a couple things. Number one, because we don't have free rotation around that double bond, they are fixed in either the cis or trans configuration. Okay, so if we have substituted dienes, we can say that they can be both in this trans configuration, like we see here, both in the trans configuration, or both in the cis configuration. And of course, if they're substituted more than twice, we have to think about whether it's E or Z. And again, go back to chapter 11, chapter 7 to remember how to prioritize E and Z. By the way, E and Z prioritization is also on the nomenclature review that I just posted on Tracks and Canvas. Okay, so in this case, here we have our trans-trans. In this one, we have our cis-cis. In this opportunity, we have our cis-trans, okay? So what we'll see from this is that different configurations give different reactivities. But these are all unique stereoisomers because, again, we do not have free rotation on our double bond. Okay, so, but we do have rotation on that single bond between those two double bonds. So because that sigma bond has free rotation, we actually have conformers available. They can be in one conformation or the other conformation. If the two double bonds are on the same side together, we call that the S-cis conformation. Okay, the S denotes that our double bonds are the parts that are together, okay? Then we also have our S-trans configuration where they're on the opposite sides like this, okay? So in some reactions, the S-cis configuration is required. And in some reactions, it doesn't matter. It'll react as the S-cis or the S-trans, okay? So we need to think about that if we cannot manipulate the double bond, we will have specific stereoisomers associated with it. For example, this cis-cis versus cis-trans, these are stereoisomers because those double bonds do not rotate. So they are discrete molecules, okay? However, if we rotate around this sigma bond here, we can make our trans-trans stereoisomer into the cis conformer or the trans conformer, okay? So we do have a difference between the stereoisomers, which are different molecules, and the conformers, which are the same molecule, just in two different configurations. So we need to keep that straight in our head as we move forward. Excuse me. So let's talk about the reactivity of conjugated dienes, okay? So there are 4 distinguishing features within the conjugated dienes. Compare them to isolated dienes. Some reactions of conjugated dienes are different than that from the isolated double bonds, okay? And we'll see that as we move forward here. Conjugated dienes are also more stable, meaning they have higher heats of hydrogenation than isolated dienes, okay? Which means that they have more stored energy, okay? So the conjugated, the less stored energy. So the conjugated dienes also absorb longer wavelengths of ultraviolet light, meaning the longer the wavelength gets, the lower in energy it is, okay? And I'll talk about that excitation of those electrons in just a little bit. The other thing we find with our conjugated dienes is that the sigma bond in between the two double bonds is unusually short, okay? And we have a reason for that, and that it has to do with its kind of its resonance stability and its resonance stabilization. So let's look at that resonance and that shorter carbon-carbon bond that's in between those two dienes. And if we look at our major conformer, our major contributor to this resonance structure, it's where we have those two double bonds and we're separated by that one single bond, okay? However, if we do a charge separation as a resonance structure where we have a positive charge on one side and a negative charge on the other, that double bond is now where the single bond was, okay? And another possible resonance contributor is where we have the charges swapped, and we still have that double bond between the 2 and the 3 carbon, okay? Now, what we learned about last time was that having charge separation and fewer bonds is actually a less stable version of the resonance contributor. Therefore, it is a smaller contributor. However, it still contributes to the overall resonance structure. Now, because this has the highest number of bonds, a total of 5 bonds, and each of these has 4 bonds and a separated charge, so this is the more stable of the resonance contributors. It contributes the most. However, because of that partial double bond character here, we see it does have our hybrid resonance structure, has that little bit of a double bond, and that accounts for the shorter sigma bond between the two double bonds, okay? And if we look about that as orbital overlap, we'll see that this, because they're planar with each other, that little bit of overlap in the center gives a little bit of double bond character. That little bit of double bond character shortens that bond, okay? So let's talk about that as a function of ultraviolet visible spectroscopy, or UVVis, okay? Okay, in UVVis, we basically are taking the light that is just above the energy of visible light and the visible light, and we're looking at ways it interacts with matter, okay? So particularly UVVis spectroscopy tells us about double bonds and how many double bonds we have associated in our compound. So our UV band is between 180 nanometers and 400 nanometers, okay? And so our wavelength starts very short at our shortest, which is 180 nanometers, and gets longer and longer and longer as we go. So as we remember about our electromagnetic spectrum, the shorter the wavelengths, the higher the energy. The longer the wavelengths, the lower the energy. So as we go from UV, it's higher energy, to the visible, lower energy. And then if we go to the IR, that's even lower in energy, okay? So they interact with molecules differently. The UV and visible will react with our electrons that are in our bonding, our highest molecular orbital that actually has an electron in it. And you can hit that electron with that wavelength of light if it's the right energy and raise it into an orbital that is not currently occupied, but once you excite it into that state, it has absorbed energy and moved into that higher excited state. Now, it will then, of course, degrade and give out light. However, the fact that it absorbed that energy tells us something about that energy level and tells you that that electron is how hard it was to excite that electron. So if it took a lot of energy to excite that electron, that means that gap is really, really big, okay? As you go to extending these orbitals out further and further, the gap between where the electron is and where it can be gets smaller and smaller. As it gets smaller and smaller, it gets easier to excite that electron into there. And that means the greater the conjugation, the smaller the gap, the easier it is. So if you go out from UV, which is higher energy, and you keep extending that conjugation more and more and more and more, eventually it'll start absorbing in the visible range, okay? So when we see this, the part of the molecule that absorbs that energy and excites that molecule is what we call the chromophore, okay? It doesn't have to be, you can only have one small part of the molecule actually absorbing energy, and it will absorb light. The rest of the molecule doesn't have to. So the part of the molecule that does absorb that UV or visible light is what we call the chromophore, okay? So we don't really have to know MO theory to know this. What we have to know is that by adding more and more and more of these resonance hybrid occupied orbitals, these where the electrons are, the smaller and smaller the gap to that unoccupied level is, and the less energy it takes to do it, okay? Excuse me. Okay, so a couple things about that and how it relates to Beer's law. Beer's law is something we learned in Gen Chem and probably a little bit in physics as well. Excuse me. Thought I got rid of that earlier. Okay, so the absorbance is related to the molar absorptivity of the compound. So the absorbance is basically how big the peak is, how much light it absorbs, okay? The molar absorptivity, and we occasionally call that the extinction coefficient, is actually independent based on the compound, okay? So one compound will have one molar absorptivity and one compound will have a different absorptivity. And what that means is that how efficiently it absorbs that light and at what concentration it starts to absorb that light. So let's say you have something with a high molar absorptivity. That means you can have a very small concentration of it and it'll absorb a lot of light, okay? And so that if you had a high concentration of it, it'd probably be very highly colored or absorb a whole bunch of light. Now, if you have a compound with a low molar absorptivity, that means that it doesn't absorb very much light and you have to have higher and higher concentrations of the material to see it, okay? So molar absorptivity is unique to individual compounds and is a relative term about how well it absorbs that light energy and how well it does not. Now, the wavelength, of course, is associated with the energy of the light, okay? So the energy that it takes to excite that is directly proportional to that wavelength, because wavelength is directly proportional to energy. So if you have a low energy beam coming in and it's not enough to excite that light, it doesn't absorb it. It just goes right through. But as you start to approach the correct energy that it can absorb, it starts absorbing that energy and exciting those electrons into their excited state, and then they diminish and even excite. And then once you go past that to where it's too high or it's not interacting, you do not see any absorbance at all. So that means the presence or absence of a peak in the UV spectrum tells us whether we do have double bonds there or we don't have double bonds there, okay? And almost always, and I say typically here, is that the more double bonds you have in conjugation, the lower and lower energy it takes, or the longer the wavelength of light will be. Okay, so let's look at that on a relative scale by starting with a single double bond and going again up and up and up. Okay, so if we look at this first compound here, ethylene, okay, that's our first and simplest double bond we can have, right? And if you look at its lambda max, its absorbance here, it actually is absorbing just outside UV, okay? UV starts at 180 nanometers, so it's just above that, okay? So we do not see a very big signature in the UV at all, okay? By adding a couple groups to it right here, these carbon bonds are changing the energy slightly, and we're just barely absorbing in the UV now, okay? And so that works for cyclic or straight chain isolated dienes. They absorb just barely in that UV, okay? Notice the alkynes and the terminal alkenes also are just barely absorbing in that UV range because they are isolated by themselves, okay? Our first and simplest conjugated diene, which is the butadiene right here, is absorbing well away, I mean, almost, 30 to 35 wave numbers, nanometers away. That's a much significant jump in the energy. And so we see it start to absorb in the UV, okay? Now, it doesn't matter whether they're cis and trans or substituted or not, they are all gonna start absorbing in that lower energy band, in that around that 200 band. But then look, if we break conjugation, it jumps all the way back up to outside the UV again, okay? So we have significant, when we have them conjugated, they are definitely starting to be absorbed in that UV band. If we break that conjugation, we lose that lowering of energy of exciting those electrons. Okay, so when we actually kind of force the materials to stay in a plane, we actually get a little bit of advantage. We actually are moving even to lower energies. The fact that they don't have a conformation that they can twist in, they're locked in that position, makes it easier for them to overlap, and that overlap is demonstrated by that lower energy needed to excite it. And then, of course, by extending the conjugation even one more double bond, we get a significant drop in energy again, and we see it moving closer and closer to the visible. So that by the time you get about 4, 5, or 6 of these together, you're starting to absorb blue light and the material starts turning yellow. Okay, so that is the part I wanted to talk to you about on chapter 13, part 2, conjugated dienes. Is there any questions about UVVis and or the fact that these things are or are not conjugated?
This is kind of what you meant about your tomato example from yesterday, right?
Correct.
Okay.
So by saying that it takes that it's a smaller gap for the electron to go to the next level, is it actually like a physically smaller gap, or is it just like less energy?
It's an electronic gap.
Okay,
so it is a smaller energy gap, but it's literally you have to add energy to that electron to make it go to its excited state.
Okay.
Okay, so that making it go to its excited state. I don't know, can you see my hand move here?
Yes, sir. Yes, sir.
Okay, so that physically making, giving it enough energy to be at that higher energy state took energy, and that's the energy it absorbed, is that amount, that equivalent to that light. Okay. Now it will go back and emit light or emit heat or something like that, and so when it goes back to its normal state, it can then absorb more of the or more of that same energy of light.
Okay.
And then just to make sure I understand the trend, you mentioned that the higher you go in energy states, the less energy it takes to take it to the next energy state?
The more things you have in conjugation, okay? So let's say you have only 2 things in conjugation, and so your energy band is going to be kind of small because you have, all the different double bond possibilities and all the different, ways to mix the electrons in those orbitals together, right?
Sure.
Let's say you add one more double bond to your system. Now you have a wider section where you can add electrons in. That energy that is between the lowest electron you have in your system and the highest electron gets a little bigger. And then let's add another one and it gets wider again. And so the energy of the electrons, the more electrons you add to the system, it gets bigger and bigger, okay? Now, as you're getting these electrons, adding more and more electrons to this area gets bigger and bigger. Well, the gap between where it can be excited now, because these imaginary orbitals that aren't occupied here are getting just as big as the ones that you're building down below. So both of these bands of electrons are getting bigger. This one has electrons in it, this one doesn't. And as they get bigger, they're getting closer and closer together. And you take less and less energy to dump from the top of one band to the empty orbital of the other.
Awesome. Thank you.
Does that make sense?
Yes, sir.
Okay. Okay, so that's why in the case of the lycopene here, let's see, there we go. See, we actually only have maybe the center of these, of the 9 double bonds here in the middle here actually are conjugated. The 2 at the end aren't conjugated, they break conjugation there. So those right there are starting to absorb so much that you only see the red color come through. And so that's the idea that we go from ethylene, which we can't see at all, even in UV, all the way to lycopene, which we see as that bright red color. All we're doing is adding a double bond, double bond, double bond, double bond. Okay? Okay, so that is our conjugated dienes and how we can see them by spectroscopy. Okay, now let's start with reactions on them and why they are different than regular double bonds. Okay, so the first thing we want to talk about is, remember that the reactions that we have of isolated double bonds, they act like just double bonds, okay? Because there's no energy difference, there's no change in them. If we added something like HBr across our double bond, we're going to get some of it reacting here and some of it reacting here. So if you only had one equivalent, you get a really big mixture of products, okay? Because they're going to add to one or the other or both. And there's no specificity for it. So if we actually used a whole bunch of HBr to make sure we hit every single one of those double bonds, we see we get the same product every time, okay? And it's controlled by our Markovnikov's rule. That's saying that the hydrogen is always going to be on the more hydrogen, on the side with more hydrogens because of the stability of our carbocation intermediate. Okay, so in the case of adding a whole bunch of excess HBr, we're always going to get this product where the hydrogens are going to add at the end and the bromines are going to add at the more substituted carbon. Okay, so the only way we can get specificity in a double bond, comparing one double bond to the other, is to have one that is a more stable carbocation. So in the case of, if we have this molecule here, we have a monosubstituted alkene, we have a disubstituted alkene. And what we know about that is the disubstituted alkene here would create a more stable carbocation. Therefore, this one would create a tertiary carbocation intermediate. This would create a secondary carbocation intermediate. The tertiary carbocation intermediate being more stable means that our chloride, our second group coming in, is going to add to that more stable carbocation. So we actually end up with a little bit of specificity because of the stability of the carbocation, not because it was one alkene is better than the other. Okay, it's the stability of the carbocation driving the major product. Okay, so this same thing does not happen when we have conjugated dienes. Okay, so again, unconjugated dienes react just like regular alkenes in chapter 8. Carbocation stability drives the product. Okay. All right, now let's move to a conjugated diene. Okay, and let's try that same reaction where we want to add one equivalent of something across that conjugated diene system and look up what the products are. So if we just add chlorine to the system, we should end up with 2 chlorines on our product somewhere, right? So one equivalent of chlorine here. There we go. Okay, so when we run the reaction, we get 2 products, okay? We get the product we're expecting, where the chlorine is adding across a double bond, just like a double bond, okay? And that's our 1,2 addition, right? We get both chlorines adding across that single double bond. But we get another product, okay? That other product is what we call the 1,4 addition, because it adds to the 1 position, and then the double bond moves over to the middle, and we get addition at the last carbon, or in this case, the number 4 carbon, okay? So which added first and which added second, that's what we have to figure out now, okay? So let's try it again where we look at, and instead of adding chlorine, which is symmetrical, let's add something unsymmetrical like HBr, okay? So when we add HBr here, we're expecting it to do, act like a regular alkene or act like a conjugated diene, okay? So if it reacts like a regular alkene, what we should see is the 1,2 addition, because the hydrogen's going to add to the least substituted carbon, the bromine is going to add second and add to the more substituted carbon, okay? And so we see that we get the product we desire. But we also get another product. We get our hydrogen adding to our terminal, and we get our bromine adding to the other side, and our double bond has moved over to the middle. Okay, so that means 2 things are happening here, right? So when we think about that, we have what we call our 1,2 addition, which is our direct addition. That's reacting like every other diene every other alkene we've played with so far, okay? But now we have a new thing happening. We have that 1,4 addition. We call that conjugate addition, okay? And so that conjugate addition happens because those double bonds are in conjugation with each other. Okay, so why does that happen? Well, let's go to the next slide here. The reason it happens is because of our carbocation formed, okay? So just like in every other reaction, the first thing that happens is the electrons from the double bond reach out and grab at that hydrogen and create a new sigma bond, okay? When those electrons do that, it wants to generate a carbocation, and it's going to generate the most stable carbocation it can. And so in the first step, it forms our carbocation on that adjacent carbon, okay? But in section 13.1, we learned that a carbocation next to a double bond forms an allylic cation. And that allylic cation is resonance stabilized to move from the first carbon over to the third carbon, first carbon to the third carbon, first carbon to the third carbon. And it's stabilized, right? So if we draw the other resonance structure of that stabilized allylic cation, we end up moving the positive charge. These electrons kick in here, and the positive charge ends up on the terminal, the number 4 carbon here, okay? So if the reaction progresses, it's going to go back and forth between those two resonance structures, and we're going to get our product where it can go where we first formed the carbocation, or it can go where we had the allylic stabilized carbocation form, which is on that 4th carbon, okay? That explains our 2 different products we get, okay? Will we have an exam review? No, we won't. We're going to have that activity. Well, we might have a little bit of a time for an exam review before the activity on Thursday. But then the exam will start at noon on Friday. Okay. All right, back to this. So the allylic carbocation here is the thing that explains why we can get a 1,2 addition versus a 1,4 addition product. Okay, so can we predict these? That's the question, okay? And we can, okay? So if we run this reaction with HBr at low temperature, the major product is going to be our 1,2 addition product, and our minor product is going to be our 1,4 addition product, okay? If we run that exact same reaction with exact same reagents at a higher temperature, the product ratio shifts, okay? We have less of the 1,2 product and one of the more 1,4 product, okay? So there has to be a reason that explains the difference in product ratios for having it done at just 2 different temperatures. And of course, drum roll please, thermodynamics. Okay, so we have to compare the difference between the kinetic product and the thermodynamic product of the reaction mixture, okay? So the kinetic product is the product that forms first. This is always the 1,2, okay? And I'll explain why in a couple slides, okay? The thermodynamic product is the one that makes the most stable final product, okay? So we have to think about what makes the product more stable, okay? So if we have a kinetically controlled reaction, that means the kinetic product is the major product because we're controlled by speed, okay? If we have a thermodynamically controlled reaction, we can wait around to make the more stable product, okay? So we have time to make the more stable product. Now, just because something is a kinetic product, it doesn't mean it can't be a thermodynamic product too, but most of the time we do see a difference between the kinetic and the thermodynamic product. Okay, so if we look at that addition of HBr across that butadiene, we actually see that the kinetic product is the 1,2 addition. However, the thermodynamic product is the 1,4 addition. Now we can have predicted that because at low temperature, the 1,2 is favored, and at high temperature, the 1,4 is favored. But why? For that, let's look at an energy diagram. Okay, so if we remember our energy diagrams here, our energy is just on this axis here, increasing energy goes up, and just as the reaction progresses, it goes in this direction here. And our starting materials start with a certain amount of stored energy, and as we proceed through the reaction, we have to go through our first activation barrier to get the addition of that hydrogen across on that double bond to generate our first intermediate. And our first intermediate in this is that carbocation. Now, because that carbocation is next to that double bond, we now have that allylic cation where it is going back and forth between those two carbons. Now, if the bromine comes in and adds on that carbon, that's the 1,2 addition. If it comes in and adds on the other one, that's the 1,4 addition. Okay. So, because the bromine is right next to where that carbocation is, we have a lower activation energy to have that bromine attack at the number 2 carbon. Okay. But it takes slightly more energy for the bromine to wait and move over to attack at the 1,4. So there's an actual higher activation energy to get to the 1,4 product. Okay. So if it's less energy to get to the 1,2 product, what would the product be? Well, the product ends up being this right here, our 1,2 addition, and we have a monosubstituted alkene over here. Okay. However, if we can add a little extra energy to it right here, we actually end up with the 1,4 addition product. Now the 1,4 addition product has a disubstituted alkene. Disubstituted alkenes are more stable than monosubstituted alkenes, and therefore it has less stored energy, and it is the thermodynamic product because it's the more substituted double bond. Okay? So let's talk about that in a different way. Okay? So if we want to talk about the kinetic control of the reaction, the way we're going to do that is we are going to force it to go to that 1,2 product. And to force it to go to the 1,2 product, we typically lower the temperature. Okay? The reason this works is that once we form that 1,2 product, that 1,2 product at a low temperature does not have enough energy for it to reverse and go back to that intermediate carbocation. So we call the reaction irreversible, and therefore the product that happened first is the predominant product. Okay? So at low temperatures, we cannot reverse the reaction to go back to our reactive intermediate, and therefore we always get the kinetic product, or the fastest product, as the major product. Okay? So what about the thermodynamic product? Okay? If we had thermodynamic control, we have enough heat that we can make the reaction, once we form products, go back to that reactive intermediate. That means that the product formed is going to keep going back to the reactive intermediate and then go back and forth till you get to the product that is the more stable product. Okay? So in an irreversible action, you don't have enough energy to go back up that energy barrier. So in the irreversible reaction, we don't have enough energy to get back to this activation, to this intermediate here, and we stay at that energy barrier. But if we added more heat, all we'd have to do, notice we can get back to this intermediate and then come back down to the more thermodynamically stable product if we have enough energy to get back to that intermediate. Okay, so if the reaction's reversible, that gives us time to make the more stable product, because the less stable product can go back to that intermediate and get back. So let's look at that one more way. Why are 1,4 addition products typically more stable than 1,2 addition products? And I gave you a hint because I told you the more stable, the more substituted alkene is the more stable alkene. Okay, so in this case, the kinetic product is the 1,2 because it happens faster, but the 1,4 is more stable because it's more substituted. Okay, so why are 1,2 products typically formed faster? Okay, and it has everything to do with proximity. Okay, when you first have the double bond reach out and grab the hydrogen and create that new sigma bond and form that carbocation, the remaining bromide is sitting right next to the carbocation being formed. Okay, so it is right next to a positive charge. It has a negative charge. It's immediately attracted to that to form that new sigma bond. Okay, however, if you wait, and it would have to wait around and or transfer, actually literally move 2 carbons over to get to react to the 4 carbon, okay? So it has everything to do with the idea that it already was formed right near that carbocation, and it is electrically attracted to that carbocation. Therefore, the proximity effect is always the kinetic product, drives the kinetic product, okay? So if the 1,2 is always the kinetic product and the 1,4 is the thermodynamic product in this particular case, is the thermodynamic product and the kinetic product always different? And the answer is no, okay? Let me show you an example, okay? You can have one product be both the kinetic and thermodynamic depending on the structure of the diene, okay? So in the case of this compound here, we have our diene where we have our regular monosubstituted alkene over here, but notice this alkene right here has 2 methyl groups on it, so it's a tri-substituted alkene, okay? So it's a tri-substituted alkene to start with, okay? So it's already more stable than the monosubstituted alkene that we have on the other side, okay? So this is already more stable, okay? Now, if we were to create the 1,2 addition product, the kinetic product, we will lose this monosubstituted alkene, and we're not going to touch the disubstituted alkene, okay? So that's the 1,2 product. That's the one we expect, okay? Now, if we wanted a 1,4 addition, we're going to take away that tri-substituted alkene and turn it into a disubstituted alkene. We're losing stability. Our tri-substituted is more stable than our disubstituted. Therefore, this is not the thermodynamic product. The more substituted alkene is the thermodynamic product. Therefore, this is both the kinetic product and the thermodynamic product, okay? So we always want to look at the product as to which product is going to give us the most substituted alkene, and that will drive your thermodynamic product. Your 1,2 addition is always your kinetic product. Okay, so any questions about thermodynamic versus kinetic products in a 1,2 or 1,4 addition across a conjugated diene?
So you said the 1,2 addition is always kinetic, and then for the 1,4 it just depends on which one's more substituted?
The kinetic product is always the 1,2 addition. Okay. The thermodynamic product is the one that gives the more stable alkene.
Okay, gotcha, thank you.
It can be either. So the thermodynamic product can switch back and forth. 1,2 is always kinetic.
Okay.
Because of proximity. Okay. Okay, we're right here about 12:45. So what I'd like to do now is go ahead and take about a 5-minute break. And go ahead and I'm going to close out the meeting and reopen it so that we can come back in and it'll start translating for people who weren't able to attend. Okay, let me go ahead and stop recording.